Hello, y'all. Welcome to lesson 60 of my DP chemistry curriculum. Today we're doing structure 2.4.3. We're going to talk about alloys as they're mixtures of metal and other metals or nonmetals. They have enhanced properties. We'll talk about what that means. We'll explain those properties in terms of non-directional bonding, and we'll illustrate with common examples. Specific examples of alloys don't have to be learned. So you do not need to have these alloys memorize their composition. You just have to understand what their properties are and how those come from the type of bonds. So when we talk about alloys, the first thing we need to do is look at ionic and covalent and realize these are usually two or more elements. But when we look at metallic bonding, we've usually looked at only one element. And this has to do with that bonding, because metals will only bond within that lattice. So it's a lattice with electron bond. And that kind of changes the way we look at it. So metals, they specifically form alloys. And specifically, these are not compounds. And we're going to talk about what that means in just a moment. But from what we know about compounds, it is not two things bonded together. Alloys instead are actually mixtures. Specifically, these are homogeneous mixtures of a metal and a metal or a non-metal. It's almost like a solid solution where the solution is one thing and the solvent is the other. Or sorry, the solvent is one thing and the solute is another. And that's what alloys kind of are like. So we have a couple classic examples. One of the most common ones is steel, which is literally just iron with carbon added. One of the best old stories is that Vikings used to put bones of their enemies or something like that into their metal crafting to enhance their weaponry with the spirits of those they've defeated. But really, they did enhance their weaponry by just making an early form of steel. So it's one of those cool things. And I'm sure I got almost all of that story wrong, but it's still something I like to think about. Anyways, so with alloys, we have to go back to our metallic bonding. So once again, I'm going to repeat metallic bonding a lot. When we look at metallic bonding, it's nice to have an image of it. So I like to think of our cations, and I'm just going to drop some big ordered cations in a nice lattice structure. And you know what? I think we only need two rows of it. So we'll shrink this a little. And within that structure, we have our negative electrons. So we have this lattice plus electrons. These are all creating electrostatic attractions with things close to them, and that's our metallic bond. When we add things into it, we create two types of alloys. So as we add elements, we create two types of alloys. So the first type is what we call substitutional alloy. Substitutional alloy. This often happens when you're adding metals, but this is where an element replaces a cation in the lattice. And we can tell this usually happens with metals when you add metals because they are also positively charged. So in a substitutional alloy, what we're going to get is different atoms in here. So we'll have two different cations within the lattice. And so these are our substitutions. So they fully replace one of the atoms within the lattice. Now, there is a different type of alloy. So that's our second type, type 2. And this is called an interstitial alloy. And with an interstitial alloy, elements added will fill the vacant spots in the lattice, kind of messing with where the electrons go. So we can take our same original metal lattice right here and we'll plop it back. And now what we might get is we're going to likely get these additions. Oh, that's too small of a point. And so in this example, we have a couple added elements. So these are what we call additions. And they're inside the metal matrix, inside that lattice. A key point here is that in both cases, bonding is still non-directional. So what I mean by that is in our case up here, even if these substitutions have those electrostatic interactions, they're interacting with the electrons as part of the lattice, and they're not interacting with individual atoms left, right, up, down. Furthermore, with these additions, they may not be interacting with the electrons or the cations at all. For example, in steel, carbon is an interstitial alloy where it just fills in the little gaps between the lattice of iron cations. So the key thing here when bonding is non-directional is that as elements are added, there's still no fixed ratio. So it's not like an ionic compound. Still no fixed ratio. And alloys can have different amounts, so there can be different amounts of carbon within the steel, changing the property of the steel. So key with this is that bonding is not occurring between individual atoms because it still holds that property of a metallic bond, which is between the lattice and the localized electrons. This is why we specifically say that alloys are mixtures. Not compounds, because once again, we're not having that bonding between the individual atoms. We're bonding or kind of interfering with the lattice. So this is what will then happen to the metal. Their properties will change. So we have two properties that are often changed most when we create an alloy. So these are the common properties that are affected. The first is malleability. So malleability also goes hand in hand with hardness, so we can talk about both of them with the same explanation. When we have malleability, we remember that the lattice can just slide left and right, and we can get a shift where we have the whole thing shifted, but that's okay because bonding is non-directional. And you would think that with non-directional bonding of alloys, it would have no effect. But there comes different problems. The additions, regardless of what it is, being a different element, additions will be different sizes. And due to those different sizes, it then becomes more difficult for layers to slide. To shift / slide. So because we have that difficulty in shifting and sliding between those atoms, especially when suddenly you may have a little inclusion here that prevents it from making that shift. Or maybe this element is now smaller or larger, also preventing that shift. We end up with a less malleable alloy. So almost always we're going to decrease that malleability, and in uh, in with that layer of thought, or aligned with that layer of thought, we're going to have a harder alloy. So it becomes less malleable, but more hard. So creating these alloys almost shows you what it does to the metal. Iron is a very usable metal in that we can flex it and we can uh, flatten it into sheets. We can build with it, and we do build with it. But when we want to make it harder or stronger, we turn it into steel, which then makes it less able to be flattened or dented, and it makes it a lot harder and a lot stronger. So malleability and hardness is one of those really important properties that we see as we make alloys. The second property that gets often changed is melting point. So melting point, as we learned before, is based on the strength of the metallic bond. So when we change that bond by removing cations from the lattice or putting new elements between the cations and the delocalized electrons, increasing the distance, we are going to decrease that bond. We're going to decrease that attraction. So because it's based on the metallic bond, we know that changing elements within the lattice or introducing inclusions, additions to the spaces, the interstitial spaces, will have an effect. And the truth is that effect is almost always decreasing the melting point. So most times we decrease melting point. Those spaces are going to make that bond weaker. The different charges, or maybe no charge of the inclusion, will decrease the strength of that metallic bond. And so a key aspect in this as well is that the amount of element added also has a large effect on melting point. So you can add more of an element and decrease or increase the melting point based on where it's already at. The last property that we're not going to talk about much here, but it's good to know, is we can also create corrosion resistance. So that comes from adding certain elements, as we talk about oxidation and reduction in a later section, as well as acids. We'll talk about corrosion resistance through alloys. So for now, all you need to know is that alloys can increase the durability in terms of corrosion of elements, like steel. Stainless steel specifically will not rust, while iron will rust normally. So we have to think about that as we move forward. But otherwise, I hope this helps you understand alloys just a little bit more, specifically knowing both interstitial alloys versus substitutional alloys. So with that done, I hope this helps, and have a great day.